Hello, everybody, and welcome to today's morning session. And the speaker in this session is Ester Mariucci. Are you? Sorry. Okay. Yeah. Okay. So speaker in this session is Ester Mariucci from the Université of Versailles, which I've learned is now part of the Université Paris-Saclay. And she will speak about smart jumps of Lévy processes and their approximation and estimation.
Thank you. First of all, I would like to say Alex, small jumps of the process from speed observations and the one and our student were Versailles. So here is the table of contents. So I'll begin with a very short introduction just to fix the notation and give some of them. So the points following, so if you take the Lévy process, you are not able to write a closed form below of the process at time t. Sometimes you can, but anyway, you can never write it for the small jumps of Lévy processes. So we really wanted to understand what can be said about small jumps. So I will begin by recalling what is already known about approximation of the small jumps, and I will briefly talk about the Gaussian approximation of small jumps, but then I will tackle the problem of the non-parametric estimation for the law of the small jumps. So I will take a general Lévy process, and I will take n discrete observations of such a process. So I observe the process at time 0, delta, 2 delta, and so on. And I will introduce estimators that are optional instances that I will make precise depending on the sampling situation. So when I have low frequency observations, but also when I have high frequency observations, that is delta, the distance in time between two consecutive observations goes to 0. I will use spectral estimators, and when I will show you the risk for the estimate in the low frequency case, probably you will recognize minimax, rate of convergence if you are familiar with those. But probably you won't in the high frequency setting, because in this case the rate will depend on the behavior of the Lévy measure in a neighborhood of 0. And so this rate are no standard, and so we really need to have lower bounds to prove that actually we cannot use our estimate of the rates that we found are minimax optimal. So also I will use spectral estimators. They depend on some cutoff parameter that we choose in such a way to minimize the integrated risk. But this choice for the parameters depends again on the Coulomb-Navigator index of the process, which might be not known. And so we also need to do adaptation. So to find the parameter cutoff in a data-driven way. So I will also present adaptive estimators that are minimax that live up logarithmic graph. So I will begin by talking about full jump Lévy processes. I can also add a Brownian motion component. And if you are familiar with the inverse problem, then you can already guess that if I add a Brownian component with a coefficient which is not vanishing, then the rate of convergence will deteriorate. And this is exactly what happened, and I will give you the rate of convergence. And I will finish by some numerical examples. Okay, so here is the notation. So we have already seen in the first week of the problem that any Lévy process X, so that the lower Lévy process X is uniquely determined by the so-called triplet, d sigma square mu, and that the lower time t of any process can be is a convolution between the lower Gaussian process, the big jumps, and the small jumps. And so when Anita gave the first talk, she said, okay, we split big and small jumps, taking one as a threshold. Okay, so the big jumps are the jumps of the process, the magnitude of which is bigger than 1. In this talk, I will choose epsilon as a threshold. Epsilon should be positive, smaller or equal than 1. It doesn't change anything. So x at time t, the Lévy process with the Lévy triplet b sigma square mu will be written as sigma wt. W is the motion, sigma is the diffusion coefficient, plus a drift, denoted by b epsilon. So if epsilon is equal to 1, the Lévy decomposition b epsilon is b. Otherwise, you have terms that the Lévy measure coming from the compensator of the small jumps. Then I have the jumps. So xb epsilon will be the Lévy process associated with the big jumps of x, big with respect to epsilon. So x epsilon times t is simply the sum of the jumps of x, the magnitude of which is bigger than epsilon. X is the process, so the trajectories of x are Cadillac. For any fixed epsilon, the number of jumps of x, the magnitude of which is bigger than epsilon, is almost surely finite. So xb epsilon is nothing else than a compound Poisson process. Now the trajectories of x are Cadillac. I cannot simply take the sum of the jumps of x, the magnitude of which is less than epsilon. This is not well defined in general, but what I can do is take an eta, positive and less than epsilon, and I look at the jumps, the sum of the jumps with the interval 0t of x, the magnitude of which is between eta and epsilon, remove the mean of these quantities. So look at that as a sequence of centered compound Poisson process. And the beautiful result is the fact that this sequence of compound Poisson processes indexed by eta will converge in L2 as eta goes to 0 to some limit, which is a martingale that I will denote by XSF. So XSF, so as the quantity of interest for me today, is the martingale accounting for the center, the small jumps of x, small with respect to x. Okay, and what is also very important is that the Gaussian part of the process, the small jumps, the big jumps, are independent of each other, and they are Lévy processes. So if I know the Lévy triplet, B sigma squared mu, it's very easy to characterize the law of the Gaussian part of the process, but also to characterize the law of xb epsilon. So xb epsilon, said that is nothing else than a compound Poisson process. So xb epsilon at t is the sum of some IID random variables I from 1 until nt epsilon, and epsilon is the Poisson process independent of the jumps yi. The intensity of n epsilon will be denoted by lambda epsilon, and is nothing else than the Lévy value mu of the set where x is bigger than epsilon absolute value, and is also very easy to write the law of the yi's in terms of mu. Okay, so from the Lévy triplets, we can easily characterize the Gaussian part of the process, the big jumps, but not the small jumps, but I'll come to that later. Another very important tool that I will use today is the Lévy formula that tells us that x is a Lévy process of Lévy triplet b sigma squared mu if and only if the characteristic function at time t and point u of x can be written as exponential of minus t psi u, and psi is the characteristic exponent of the process that can be expressed in terms of the Lévy triplet. Well, now, you take a general process, you cannot say much about the density. For instance, if there is a element process will have density, but we don't have closed form of this density. Sometimes it can happen. Let's think about the Cauchy process, and we have in this case a very high improvement the density of the law at t. Sometimes we do not have closed formula, but still we have some very useful tool. Think about symmetrical stable processes. We have quite nice characterization for the law of the process. But even in this case, we cannot say anything about the law of the small jumps. I take a Cauchy process. the law of the small jumps. So the small jumps of a Cauchy process are not a stable process anymore. They completely lose properties of stable laws, and we do not have access to any useful formulas for the law of this process. So to summarize, here is the situation. We need to take the Lévy process. The Lévy process, the law of the Lévy process is the convolution between three laws. We know very well what to do with Gaussian processes and compound processes, and we have some difficulties in handle the martingale associated with the small jumps. This is a complex object, and a natural reflex is to say, okay, well, we don't know how to handle it, but maybe we can find nice approximations. We can find other models which are easier to handle, but that's, for instance, statistically, they contain the same amount of information. If you want to do so, I guess that the first thing you look at are weak limits. So you, first of all, you try to understand when the marginals of small jumps converge to something and what is the limit. And this is very well understood. For instance, Gnedenko and Kolmogorov have a very exhaustive result characterizing the limit for the weak limits for marginals of Lévy processes. So there are situations where the marginal of the small jumps of the Lévy process converge to a Gaussian distribution, for instance. And this Gaussian approximation is now quite popular. Just think about all the results of Asmussen, Kosinski, and so on. So for a while, I really wanted to understand how good this approximation is. So there is a Gaussian approximation, right? But what can I say about this approximation? So more precisely, what I did the request that I wanted to solve was the following. So we have an IID realization of x delta s epsilon. So an IID realization because I'm just exploiting the fact that XS is a Lévy process. So I take n observation of the small jumps. This is equivalent to taking the increments. Now the increments are stationary and independent. So this is the same thing as taking the statistical model associated with n IID realizations of the small jumps at time delta. When these n realizations are statistically indistinguishable from n IID realization of Gaussian distributions. What does it mean statistically indistinguishable? When I cannot build a test to separate the two samples. And if I want to answer this question, then I have to use the total variation distance, right? So I really need to have a sharp control on the total variation distance. And if the total variation distance goes to 0, then this means then I cannot build a test to separate the two statistical models.
Why is total variation?
For that, so because my point is really statistical interpretation. So what I would like to have is equivalence in the sense that I'm sure that I cannot test. I cannot build a test to choose between the two samples. And so we're beginning our investigation with Wasserstein instances. So I'm telling this history from the end. So we begin with the Wasserstein because total variation is much harder. We had results, sharp results of Wasserstein distances, but I don't have an interpretation of Wasserstein distance, and I have for total variation. So this was our goal, main goal, to really have a sharp control for the total variation distance.
And so convergence to 0 refers to n going to infinity?
Exactly. Yes. So please don't read the result. Just to tell you, I give you the result for alpha stable processes. So just to tell you that, so we have this paper with Alexandra Carpentier and where we have upper and lower bound for the total variation distance. So now we know exactly when the total variation distance between n IID realization of the small jumps and the closest Gaussian vector goes to 0. Okay. And now so the result is general, but for instance, I can give you the result when the small jumps are the small jumps of a symmetric alpha stable process, for instance.
Just so you take any time, small time, and look at
It's not small.
any time you take yes, realization of Lévy process at this time. And the Lévy process has to have a Gaussian component.
No. So that's a good point. In this, it's very hard to remove sigma in this proof, but we managed to remove sigma in this proof, and for alpha stable process, you can. Right? So what I'm saying is I take a general Lévy process. Sigma, the diffusion coefficient might be 0. Could be a poor jump Lévy process. Okay?
But then absolutely continuous distribution and this pure jump distribution, they are orthogonal.
Now, I'm not working on this Corot space. Of course, if I were in this Corot space, the problem is completely solved. The total variation distance is 1, because if I try to compare something which is with jumps and something continuous, the total variation is 1. But I'm taking the discrete observation, which is much harder now. I'm not on this Corot space anymore. I'm really taking the discrete observation of the process. So I look now. I have just small jumps, okay, and I take realization of the small jumps at time 0, delta, 2 delta, 3 delta, and so on. And this they can converge.
So sir, your observations are on the lattice, not continuous. Oh.
Yes, correct.
So your discretization means on the lattice of.
Yes, I am in Rn.
In
Rn.
No, R is
N
not.
observation.
But R is not lattice. R is it's real.
So time is a lattice, space is continuous.
So I'm just taking. So
I shouldn't.
I suppose that it's modelization, right? I suppose that my data come from the realization of a continuous process, but reality is such that I cannot observe the process in continuous time. I'm just
Fixed time. To take a fixed time. So your realization of Lévy, if you have Gaussian component, is continuous random. Is realization of continuous random variable.
yes.
And if you take only a small jump process, so yes, so if sigma is 0,
Yes.
then this is a discrete, yes, random variable, and you compare it with continuous random variable, and total variation distance between discrete random variable continuous is 1.
No, that's the point. That's the really important thing.
Because of small jumps.
Because what it counts in Gnedenko and Kolmogorov is very clear. What it counts is not if you are in this Corot space and you want to control the variation, you have to control a part, the Gaussian part, and the jumps, right? This is not what happens when you have discrete observation. You have to control convergence of the drift and a Dirac 0 for the diffusion coefficient plus the variance of the small jumps. Right? And if you have small jumps that are active enough, they will play the same role as a diffusion.
So if the first moment is infinity, then you have the second moment is infinity.
No. The small jumps, they have all moments because I'm truncating.
No, of the measure.
Yes, but
the
the
measure.
measure of the Lévy method,
Yeah.
the small jumps are in minus epsilon, epsilon.
I know, but so we're talking about intensity.
Yes.
Intensity.
Density can go to infinity.
Yeah, that's what. Yeah, this is if the intensity is.
But it doesn't need to.
But it could.
Yeah.
Right.
Then total variation this is okay, but if intensity is bounded, then you cannot do it.
No. I mean that's the point. I really can. So there are cases when the total variation distance goes to 0, and actually, so if you don't have the Brownian component, it's really hard. But you can look at the paper. It's really a very long paper. You can do that. And for instance, if I take alpha stable processes, here is the result. And we have also lower bounds. So this gives you exactly what is the quantity that must go to 0 in order to have that the total variation distance goes to 0. So the distance in total variation between the n observation of the small jumps, and it's not exactly, this is not always the closest Gaussian random variable, but just for simplicity, is of order of square root of n, epsilon to the power alpha divided by delta. Epsilon is where we cut the small jumps, alpha here, don't think about the movement I need to be asked, okay? So what does it mean? It means that epsilon should be really, really small if you want to be sure that you cannot distinguish between Gaussian random variables and the small jumps. So epsilon should be smaller than delta divided by square root of n to the power 1 over alpha, or symmetric alpha statements. The result is, of course, better if you have sigma, which is not 0. The rate of convergence is better, okay? So this is just a motivation this was a motivation for us to say, okay, well, actually this Gaussian approximation doesn't work so well. It really depends on the sampling scheme. And for instance, if we have high frequency data, we don't see why we should do this Gaussian approximation. So let's try something else. So we have also other ideas for approximation, but this is not what I would like to talk today. So today I will now tackle the problem of estimation, how to estimate the law of the small jumps. And just for completeness, we also have the results with Marcus Rice with Wasserstein convergence, okay? But this is weak. Okay, so now let's skip to the estimation procedures. So the data that I have are the increments of a Lévy process.
So again, yes. So it means the discrete component of your process position, or distribution is there is no discrete component. There is no discrete component because yes, every distribution of a random variable may be represented as a composition of a mixture of 3 components.
Yes.
Absolutely continuous with respect to the back measure,
Yes.
discrete, and the last one.
Yes.
So you have the last one essentially here. You cannot have absolutely continuous with respect to the back measure. No.
Yes, I can have it.
It's continuous.
Absolutely continuous with respect to
No,
Lévy.
so if you just jump process, you can see the Lévy component with small epsilon. They have it's absolutely continuous with respect to the back measure. Yeah.
Yes. Yeah, if I take an alpha stable process, right? So it has a density with respect to the back, and now I show you that the density of the small jumps is
On the
infinite.
jumps. Okay.
So there's no problem with that.
Yeah, if there's enough activity, it's going to be nice.
Yeah. I understand. Yeah. I just did.
Okay, so now I take a Lévy process, the general Lévy, so not the general one. Let me start with pure jumps. So sigma is not in there. Okay, so I'll take, if mu is of infinite variation, so think alpha bigger or equal than 1. If you think about stable processes, I would like to have Lévy processes with Lévy triplet 0, 0 mu. And if nu is of finite variation, I prefer to include in the theory also subordinators. So I just look at processes that at time t can be written as the sum of all the jumps occurred up to time t. Okay, so this is just to say that I have to put this drift, but you can forget about this drift. Yeah. Okay, so I take a per jump Lévy process and I observe the process at time delta, 2 delta, 3 delta, and so on. The last time of observation is n delta. Then I take the increments, it's the same thing, just to exploit the fact that these increments will be stationary and independent. I want to estimate from the discrete observation of the Lévy process, what I want to estimate is the law of the small jumps of the Lévy process. So I have an inverse problem. I'm not observing realization of the small jumps, I'm observing realization of the Lévy process. And in order to do that, I need 2 assumptions. So first of all, I need that the Lévy measure is absolutely continuous with respect to Lebesgue. Okay, so I will denote by P the Lévy density. It's not a strong assumption. I just, for instance, alpha stable Lévy processes and so on. And then what I need is a lower bound on the behavior of the Lévy density in the neighborhood of 0. I'm not asking that the Lévy measure behaves like an alpha stable process, for instance, but I need some control on the behavior of the Lévy density in the neighborhood of 0. And so what I call the assumption A and alpha is the fact that there exists n positive and alpha between 0 and 2, such that for any eta between 0 and epsilon, the variance of the small jumps with respect to eta is always bigger than m eta to the power 2 minus r. What does it mean? It means that the Lévy density must be lower bounded by an alpha stable like density in the neighborhood of 0. This is the assumption. I take epsilon between 0 and 1, and I denote by G delta the density of the small jumps, plus eventually this drift if I want to have subordinators in this area. And what I want to do is to assess, so to estimate G delta and assess the quality with respect to the integrated L2 loss for low frequency data and high frequency data. I want to estimate the density. The first question that probably I have to ask myself is, what is the regularity of the density? If X satisfy the assumptions, so A and alpha, then X has a density which is C infinity, and is also very easy to have a quite sharp control for the subnorm of the density and all the derivatives. So what is the situation if now I have low frequency data? Delta is fixed. What we are facing is actually a usual deconvolution problem where the target density is super smooth, it's infinity. When delta goes to 0, when we are in the high frequency setting, the situation is more intricate because now I have a double asymptotic, L goes to infinity and delta goes to 0, and I cannot rely on the existing future. Okay, let's start with delta fixed. Low frequency case. What I can do, I can use the convolutional structure for the law of its delta. So the characteristic function of x delta is the product between the characteristic function of the small jumps and the characteristic function of big jumps. Now, in this case, so the precise case of Lévy processes, it's very easy to see that the modulus of the characteristic function of the big jumps is always strictly positive. So I can divide by the characteristic function of the big jumps, and I can say that the characteristic function of the small jumps is the quotient between the characteristic function of x delta and the characteristic function of the big jumps. I can very easily, from the data that I have, estimate the characteristic function of x delta. I just take the empirical counterpart. And now, for the low frequency setting, I need to assume that we know the characteristic function of the big jumps, meaning that we know the Lévy measure on the set minus epsilon, epsilon complementary. Okay, we know the Lévy measure outside 0. So I have an estimator for the characteristic function of the small jumps. Fourier inversion theorem. I can propose an estimator for the density of the small jumps using a cutoff parameter, right? Well, and then what I have to do, I have to assess the quality of the estimator. I have to try to control, for instance, the integrated edge risk. So the result that you find here is not asymptotic. So what we have is that the integrated edge risk is bounded by, here you have the square of the bias, as edge risk, plus the variance term. Then we would like to know what is the rate. To find the rate, we need to find the optimal choice for the cutoff parameter m that minimizes the risk. And this is of order of log n divided by delta to the power 1/2. You plug in this choice for m, and this is the rate of convergence that we have. So if delta is fixed, the rate is log n to the power 1/α divided by n, which is the minimax rate of convergence for inverse problem with super smooth density. And the log is there. Now, you could also say, well, but this gives us a rate also in the case where delta goes to 0. And this rate now depends on delta to the power 1/α, which is not a standard rate of convergence. We should understand if we can do better or not. But in the high frequency setting, there's no point in assuming that we know the Lévy measure of the big jumps. We can remove this assumption. If delta goes to 0 now, then we can say that actually the law of the small jumps is close enough to the law of x at time delta. And just try to use an estimator for the law of x delta should be minimax also for the estimation of the small jumps. This is an idea, we have to prove it, right? So this is what we did. We now, in the high frequency setting, we take the spectral estimator, which actually estimates the density of x delta, and we look at the integrated L2 risk. So the upper bound that you see here holds under the assumption that delta epsilon to the power minus alpha is smaller than 1. So you need some condition on delta. Delta cannot be too big. In the paper, this is not the assumption that we put. We put an assumption in terms of delta lambda epsilon, which is more meaningful because, you know, it's the intensity of the Poisson process. But just to have easier formula for representation, and this is equivalent to delta lambda epsilon smaller than 1 if you have alpha stable processes. So again, we have the square of the bias, the variance term, plus a new term that tells us that this is a good thing to do only if delta is small enough. Otherwise, it makes no sense to have this kind of approximation. I have to find n in an optimal way, and the rate of convergence that I find is this one. So this tells us that if alpha is bigger than 1/2, then we have the previous rate of convergence. Otherwise not, but this is moral. If alpha is too small, we don't have enough jumps, then this is not a good approximation to estimate the small jumps. And we need something else, for instance, a plug-in estimator for the characteristic function of the big jumps, in this case, which is 2. Okay, so now I have this rate of convergence, and so we were quite confident that this was the right rate of convergence because we also tried kernel estimators and found exactly the same rate of convergence, but we need to prove a lower bound, which is actually quite tricky. So here is the lower bound. I take alpha between 0 and 2, and delta smaller than some constant depending on alpha, but which is very explicit. Then for n log square delta big enough, the infinite over all possible estimators of the density of the small jumps of the supremum over the estimators for the density of the small jumps that satisfy our assumptions of the integrated L2 risk is always bigger than a constant divided by n delta to the power 1/alpha. So this means that we are minimax optimal up to a log factor. And we don't know where the log is. So we have so we think that the log is missing here in the lower bound, that we must have a log, but still is not clear because there are no, so we don't know if the log is too much in the upper bound or is basically the lower bound. We cannot really rely on the existing literature, but our guess is that the real rate of convergence is with the log. Okay, now I don't know if you are familiar with proving lower bounds in a non-parametric setting for densities. So typically you can just use the Chebakov method and so on and try to build different hypotheses, or you can test, but this is not the proof that we decided to propose. So the proof is atypical. So I would like just to give you the ideas that are behind the proof for the lower bounds. So I would say that the main steps are 4. So first of all, what we do is that the problem of estimating the density of the small jumps is from indirect observations is harder than the problem of estimating the density of the process from direct observations, which is quite straightforward. So the first step consists in passing from an inverse problem to a direct one. The second step consists from passing from a direct non-parametric estimation problem to a parametric one. So what we are saying is that now, so the first step is to say I need to show a lower bound for the infimum over all possible estimators for the density of the small jumps on the class. So what we did, we take the class of density that behave like a symmetric alpha stable process. This gives a lower bound. When we are working with the class of symmetric alpha stable processes, the reflex is to say, okay, then in the end, what I have to do is to estimate alpha. Okay, so the lower bound is the infimum of the constant over all possible estimators of alpha, of the supremum for the alpha 0 in the neighborhood of alpha that you need to choose well, because now you have a double asymptotic in n and delta, of the risk for the estimation of the density for an alpha edge stable Lévy process and an alpha 0 stable Lévy process. We have the integrated edge risk, so we have Parseval that helps a lot, so we can pass from densities to the process to go the difference of characteristic function. So when we are there, we really need now to have a sharp control for the risk between a alpha edge stable Lévy process, so alpha edge here is random, and somehow the closest alpha 0 stable Lévy process. So we did that. And in the end, what we get is 1 divided by n delta 1 over alpha. This guy, so the infimum over all estimators of alpha of the soup, in the neighborhood of alpha of the expectation of n log square delta alpha at minus alpha 0 square. So once you are here, you say, okay, well, we should be close to conclude, because now what we have is really a parametric estimation problem. And we know a lot of things for stable distributions. So what we know is that they satisfy the LAN property, the local asymptotic normality. So Masuda proved that. And we have the book of Ibrahimov and Ashminsky giving a lot of lower bounds for parametric models under the LAN condition. So what we really needed to find is the rate which, so when you do the LAN property, what is the right rate, but actually this was done by Masuda. And so using these two ingredients, we can say that this guy is always bigger than a constant, and so the rate of convergence is at least 1 divided by n delta 1 over. Okay, so we are minimax up to a log factor. This was for the small jumps, but of course I can use this result also to prove the minimax rate of convergence for the estimation of the density of a Lévy process in a direct problem, okay, which was also unknown in the literature. So now if you ask me what is the minimax rate of convergence to estimate the density of a Lévy process from n observation sampled with a sampling rate delta, this is the rate, okay? So it's 1 divided by n delta 1 over alpha, where alpha plays the same role as the proof target index, or if you prefer, is the tail, so it's the exponent of the tails. Okay, now the m that I used to compute the rate was kind of log n divided by n delta 1 over alpha, so it depends on alpha. And we don't know alpha in general. So we need to choose m in an adaptive way. And that given way, this can be done. So what we proposed is a penalization procedure inspired by a paper of Valentin Chenou also. Okay, so we minimize the contrast function plus the penalization, and of course we take the penalization as the same order as the values. And what we get is that the integrated edge risk for the adaptive estimator is always less than. So this is simply what we had before, right? Is the square of the bias plus the variance term plus C over n. And 1 over n is faster than what we had before. So this means that the adaptive estimator has the same minimax rate as the estimators that we have already provided. Well, the main tool is to adapt Talagrand inequalities to the set. Okay, now What about the estimation in presence of the Brownian motion? Of course, this is quite hard because if now I add a Brownian component, I have three asymptotics: sigma, delta, and n. And it does not end, so it's really huge. We have, I don't remember, like 12 different rates of convergence. But the idea how to estimate is pretty clear. We do the same thing, right? Because if I add a Brownian component, I still have a convolutional, so I can still exploit the convolutional structure. So I write the characteristic function of x delta as the product of three characteristic functions. And if I know sigma, it's very easy to estimate the characteristic function of the small jumps and to propose a spectral estimator for x delta x. So it's the same idea, but what is difficult now is to control the risk. We can do the theory. So again, I can control, I have an upper bound for the integrated to X risk is the same bias as before, exactly the same, plus what is different is the bias, is the variance term. Okay, just to give you an idea, I put the result for alpha equal to 1. Alpha equal to 1 is somehow the easiest because of the efficient process. So we have very nice formulas in this case. And I give you the rate of convergence in two different cases. So if delta and sigma are fixed, it's the worst case, right? Then the rate is very, very slow. It's exponential minus a constant square root of log n, but this is minimax. We are in a classical inverse problem with the Gaussian modes. If sigma goes to 0 quick enough, and quick enough is in terms of the rate of convergence that we already have, then the rate of convergence is log n divided by n delta, which is exactly what we had before because alpha is equal to 1 right now. But of course, you have a lot of others. So you have many other rates of convergence depending on the relationship between sigma, delta, and b. Okay, I think my time is up. So just want to say that we also had
Three more minutes.
no, but I'm done. So just to say that we did also simulations. And so here are the pages. If I take alpha stable processes, these are non-symmetric alpha stable processes. Here, so what you have in the columns is the Blumenthal-Gator. So the first column is 0.7, the second is alpha equal 1.1, and the third is alpha equal 1.7. And in the lines, we have the dependency on time. So delta equal to 1, delta 0.1, and delta 0.01. Okay? So for delta equal to 1, we have the impression that is not working very well. But this is absolutely normal because we have a constant in front of the rate of conversion, which is exponential of 4 lambda epsilon delta. And if delta is fixed, and we take, for instance, alpha stable process, lambda epsilon is big. So, and then it works much better if I take tempered stable processes, because then this constant is not so big anymore. And otherwise, the results are better when delta is like 0.1 than delta equals 0.01, because the rate will, so the rate is faster when delta is big, because it's 1 by the n delta 1 per alpha. Okay, so all the simulations are consistent with the results that we found. So I have also like sigma, and of course, it's sigma here, for instance, is a Cauchy process basically the Gaussian. With sigma wt, and already for sigma equals 0.5 and delta equals 0.1. But this is the behavior of the estimator. It's not good, but it cannot be improved. That's just because it's an inverse problem. Delta fixed. Okay, that's all. Thank you very much for your attention. And here is the report.
Thank you very much for your talk. Are there any questions?
I'm sorry, I apologize for my stupid questions. My question was, let me see. You have a jump component, Lévy jump component. Is it for, yes, is it for, assume that Lévy jump component has yes a distribution which is orthogonal to Lebesgue measure.
Okay, this is not covered by this.
Yeah. So
Yeah,
in this
okay.
case, in this case, that's what I was thinking about that. Yeah. In this case,
if you do not add the Brownian component,
So, yeah.
you don't have convergence.
yeah, that's what I said. I was
Yes.
thinking of Brownian component. Yeah, or not Brownian, but absolute continuous with respect to Lebesgue
Exactly.
measure.
So
Yeah.
in this
Spread
case,
out
if the
need-
Lévy measure is not absolutely continuous with respect to Lebesgue and sigma is 0, the total variation does
Yeah,
not
that's
go
what
to
I meant. Okay, thank you. Thank you. So
Yes.
yes, I was thinking about that, trying to construct
no,
examples,
that's
but because I was thinking, okay, I'm fine.
Yeah. Under what circumstances would you know the density of big jumps but not the small jumps? What
Sorry.
you said that for your estimator, you knew the characteristic function for the big jumps.
So what I'm
Well-
saying is that if I knew the Lévy triplet, even if I knew the Lévy triplet, I could not say anything about the law of the small jumps. Right?
Right.
But if I know the Lévy triplet, I know the characteristic function of the big jumps.
If you know the Lévy triplet, you would know the characteristic function for the whole process, and you could just
Sure.
divide that by the.
No, but because you do inverse theorem, of course, but still it's crazy tricky. I mean, look at the
Yeah.
formula that you get, it's not informative. So our point is that, so that is fixed. If you assume to know the Lévy measure outside 0, you can say something nice somehow about the law of the small jumps. Still you can, right? And of course, what you could ask me is why you don't plug in an estimator of the characteristic function of the big jumps. We tried, of course. So it works for delta, not so small, but smallish. Otherwise, we don't know what to do. So what we can do, of course, is to plug in an estimator for the Lévy density. So we had a minimax estimator for the Lévy density, and I could plug in that in there, but then we are not able to find a minimax rate of convergence.
Sure. And for the high frequency, you went very quickly past the slide on the high frequency estimation. What was the different estimator? Slide 14, I
Oh
think.
no, it's just, so the one I show you is just the estimator, so you just remove the denominator, the characteristic function of the big jumps. It's nothing else than an estimator for the law of mistake. If delta goes to 0, you can plug in an estimator for the characteristic function of the big jumps. It works well, but we don't see the point because the rate of convergence is already minimax. So
Okay. Yeah, I understand. Thanks. Yeah.
You don't have access to sigma, I guess, in the latter part of your talk. You also need to plug in some estimator that has certain
So
convergence.
you have no idea how long it is to compute the rate of convergence for sigma node. So of course, you can do that. At the beginning, we were so confident, just put, for instance, an estimate for the Blumenthal index and do in a completely data-driven way. It does not work because the rate of convergence to estimate the Blumenthal index is lower than that.
Yes.
So something that one could try to do,
But
but it's really.
So just a quick question. So your estimator, so you take the L2 norm squared. You estimate, you get a function of x. You have the function that you want to estimate. That's also a function of x. You look at the difference and then you integrate over all x, and then take the expectation with respect to the observations. Is that right?
Oh, so I take, so here it is.
What? Yes, right.
Yeah, so this is the expectation of the integral of g s delta x minus delta x squared
Squared.
dx.
Yes, that's right. So you integrate over x, and then you integrate the randomness out, right?
Right, is the expectation, right.
So what
Yes.
happens if you change the norm?
Then Parseval is not there
Exactly.
anymore.
Exactly.
You can do that.
But
but
you
it's-
shouldn't. There shouldn't be difference, right? I mean, the
No,
estimate
it's
is
just,
still-
it's just technical. So it works with P. Okay, so it's just that it's much more longer to write, but the shouldn't change the rate of convergence.
Mhm.
With another loss, I don't know. LP loss shouldn't change the rate of convergence. It's just that it's much more convenient to work with L2 because of Parseval.
Yeah.
But it's really not so important because, so we didn't write in the paper, but we did in parallel all the computations also with kernel estimators. And there is much easier to use LP, so it's not a spectral estimator anymore. You can use LP loss, the rate are the same. With other loss, I don't.
And when you talk about the direct estimator, that's when you actually have the small jump process separated, is it?
No, it's just it's the direct in the sense that what I observe are the observations of X. So from observation of X, I want to estimate the density of the X. So for me, this is the direct.
Oh, I see.
Is the direct problem because the other one is indirect, is inverse because I don't observe so realizations of the small jumps, but only of the entire process.
Understood, yeah.
Other questions? There are no more questions. Then let's thank Esther again for her talk.